Hi everyone, this video is a backup of my talk, so can you hear me? Well, actually, if you see this, it means that I cannot connect to the internet now, but I'm sure that I'm now trying to be back for the discussion, so hopefully see you soon. Thank you so much for inviting me, John. I'm Shohei Shimizu, Shiga University and LiNGAM. Today, I'm going to talk about the LiNGAM approach to causal discovery. Uh, oh. First of all, I'd like to briefly explain what is causal discovery. Causal discovery is a methodology for inferring causal graphs from data. But causality does not come up from data without making any assumptions. So we make some assumptions and combine them with data to infer a causal graph. Causal graph represents the causal relationships between variables. This is our example causal graph. And for example, assumptions. Assumptions are made in terms of the following. So first, we may ask whether the functional form is linear or nonlinear, or maybe the function belongs to some particular class of nonlinear functions. So another assumption is about what kind of distributions observed variables follow. So are they continuous or discrete, or which class of distributions do they follow? So also we need to decide if we allow hidden common causes or not. Further, we need to decide to assume if the causal structure is acyclic or cyclic. Then we combine these assumptions with the data to infer the underlying causal graph. So causal graphs are the key to statistical causal inference. For example, when estimating the causal effect or the intervention effect, we need the information contained in the causal graph. For example, if we know the causal graph, we can use the backdoor criterion, for example, to select variables to adjust for. For example, the figure on the right, this one, is a scatter plot of the chocolate consumption and the number of Nobel laureates of 23 countries. Then suppose that this causal graph is correct. Then this graph tells that we should adjust for GDP to estimate the intervention effect of chocolate consumption on the number of Nobel laureates. The information contained in the causal graphs is, also recently proving to be useful also in machine learning. For example, the information in causal graphs containing causal graphs can be used for better domain adaptation, and is also useful for checking and improving the fairness and interpretability of machine learning models. So how do we draw a causal graph? The current most common way to draw a causal graph is to use background knowledge. but we don't always have enough prior knowledge to draw causal graphs. So we often need to use both data and background knowledge to draw causal graphs. So causal discovery is a methodology for inferring, estimating causal graphs from data. Suppose we have reduced the number of candidate graphs to these three causal graphs based on our background knowledge, but we don't know any more about which is correct, which is better than the others. So in this kind of situation, we use causal discovery. We use causal discovery to use the data to find out which of these three is better than the others. The causal discovery is a relatively new tool for causal reasoning, but it has been used to search for causal hypotheses in the following fields. For instance, epidemiology, economics, prevention, medicine, chemistry, neuroscience, and climatology, and so on. So more papers have been published in these fields as well as other fields. So you can find those papers on this URL. So causal discovery is one of the challenges in causal reasoning. So the classical non-parametric approach, it uses conditional independence to infer causal graphs. The non-parametric approach makes no assumptions about distributions or functional forms, but it has a limitation. It can only find a class of equivalent models called the Markov equivalence class. And in many cases, the causal direction cannot be inferred from data. To go beyond the limit, we need to make additional assumptions. For example, we make restrictions on functional forms and distributions, or either of which, or both. Then, under such assumptions, sometimes we can uniquely identify the causal graphs, or at least we have some small number of equivalent models than that included in the Markov equivalence class. Of course, we need to make reasonable assumptions, but this is a very useful feature if we can make reasonable assumptions, depending on our datasets. So the LiNGAM model is our example of such an identifiable model when making such additional assumptions, The LiNGAM model assumes that variables follow non-Gaussian continuous distributions to take advantage of statistical independence between variables. The model assumes linearity and acyclicity, but many extensions have been proposed to relax their assumptions. For textbook and survey, please refer to these references. So now let me introduce the causal discovery methods in some more detail. So first, I will explain the framework of causal discovery. We use the framework of Julia Powell's structural causal model. In this framework, each variable xi is a function of its parent on the graph, on the causal graph, and our error variable ei, it includes all the other variables than the parent together. So then in this framework, we make some assumptions and try to find a causal graph that satisfies the assumptions we make and also is consistent with the data. So a typical example of assumption is the assumption of a directed acyclic graph and the assumption that there are no hidden common causes. This means that all the common causes are measured or observed. And the second example also assumes a directed acyclic graph of observed variables and hidden common causes, but with the assumption that there may be hidden common causes. Next, let me introduce the non-parametric approach to causal discovery. This non-parametric approach uses conditional independence of variables to infer causal graphs. In this approach, we want to investigate to what extent we can infer the underlying causal graph without making any assumptions about the functional form or distribution. So to illustrate the idea of the non-parametric approach, we take an example of two variables. This approach does not make specific assumptions on functional forms or distributions, but it doesn't mean that it doesn't make any assumptions. Typically, this approach assumes directed acyclic graph and also assumes no hidden common causes, as other approaches do. Then we try to find the causal graph that best matches the data among the graphs that satisfy the two assumptions. For example, let's consider the case of two variables. In this case, these three graphs satisfy the assumptions of the directed acyclic graph and no hidden common codes. Then if X, and we have some data, and we collect some data, and if X and Y are independent in the data, we choose graph C on the right, because in graphs A and B, X and Y are not independent, but in graph C, only in graph C, they are independent. On the other hand, if X and Y are not dependent in the data, we choose graphs A and B, and we don't take C. So now we have two candidates, but we cannot further distinguish between the two graphs A and B because X and Y are not independent both in graphs A and B. This is consistent with the data. So like these two graphs, A and B, the set of models that cannot be distinguished in terms of independence, and the conditional independence are called the Markov equivalence class. So this non-parametric approach has been extended in many directions. In the current example, we have assumed that there is no hidden common cause, but it has been investigated how the equivalence class would be characterized if hidden common causes are assumed to exist, or if the data are time series, or if the structure is cyclic rather than acyclic. Basically, basically in this approach, the causal graph is often not uniquely identifiable. So, for instance, we cannot estimate the causal direction in this case. So now let me introduce another approach other than the non-parametric approach. This approach makes additional assumptions on the functional form or distribution. In this approach, we want to investigate what assumptions make causal graphs identifiable. So, when we make some additional assumptions about the functional form and distribution, more information becomes available than just the conditional independence of variables. For example, take a look at these two graphs. There are two variables, x and y, and their causal directions are opposite. In this case, x and y are dependent in both of the cases, so the two causal graphs are indistinguishable in terms of conditional independence. However, for example, if we make the assumptions of linearity and non-Gaussian continuous distributions, we have shown that these two models have different distributions. So here, for the sake of illustration, I used a uniform distribution as the non-Gaussian distribution, but the same is true for other non-Gaussian continuous distributions. We use this difference in distribution to infer the underlying causal graph from the data. This was a two-variable example, but the same applies to cases with 3 or more variables. So now I will introduce the LiNGAM model, linear non-Gaussian acyclic models, as a representative example of identifiable causal models. This model assumes linearity, non-Gaussianity, and acyclicity. We further assume that there are no unobserved hidden common causes here. So Ki represents the causal order of the variables xi, and the other variable ei, they are assumed to be independent and non-Gaussian. And this assumption of independence implies that there is no hidden common causes. Then we have shown that the coefficients Bij and the causal order K, they are identifiable in this model. We can draw the causal graph based on the zero non-zero pattern of the coefficients B. So the causal graph is identifiable in LiNGAM model. Okay. Okay, so now I will explain how we use non-Gaussianity and independence in more detail. First, let's assume that the underlying model in the model is the model in this blue box, the underlying model. In this model, x1 is the cause and x2 is the effect. Cause, effect. In this case, we can, suppose that we regress the effect x2 on the cause x1. Then the residual here. Then we can show that the explanatory variable x1 and its residual, they are independent. On the other hand, if we regress the cause x1 on the effect x2, we can show that explanatory variable x2 and the residual, they are not independent because both of them have E2 error variable E2 in them. So this introduces in some dependency between the two. So in other words, when we regress according to the direction of causality, the explanatory variable and the residual become independent. But when we regress according to the opposite direction of causality, the explanatory variable and the residual become not independent. They are not independent. So we use the difference, independent and dependent. We use this difference to find the direction of causality. So okay, so I will further explain the reason why non-Gaussianity is necessary. So first, the residual and explanatory variable, they are always uncorrelated when doing ordinary regression. But if the variables are Gaussian, uncorrelatedness is equivalent to independence. So the explanatory variables and the residual, they will be uncorrelated and independent for both directions. So they are uncorrelated and independent for both directions. So we cannot distinguish between the two causal directions for Gaussian variables. Okay, so to take advantage of statistical independence, we need non-Gaussian assumption. And then we need to measure independence to compare the two models. So a typical way is to compute mutual information to measure independence. But computing the mutual information is computationally not so easy, so we use the following trick. So assuming the LiNGAM model is correct, we can compute the difference in mutual information between the explanatory variable and the residual of two models with different causal directions by computing these one-dimensional entropy H. So one-dimensional entropy is easier to compute than mutual information since it does not require complicated two-dimensional statistics. So it is relatively feasible to measure independence in this case. Next, I will briefly discuss how we could evaluate estimated causal graph. So first, we have several things we can do before estimating the causal graph. For example, we can use the normality test, Gaussianity test, to evaluate the validity of non-Gaussian assumption. We can also examine the validity of the assumption of continuous distribution by looking at the histogram of variable. Well, the point is, even if a distribution is continuous in principle, in practice, it could happen that the distribution is close to degenerate distributions. For instance, sometimes almost all the values are zero. It could happen sometimes. So we should check it. So third, there could be variables pairs that may have a very high correlation with each other. Sometimes they measure the same thing, or sometimes once one variable is determined, then the other is automatically determined. In such cases, we could omit one of them, or perhaps we should use some latent variable model to model the high correlation. But maybe omitting one of them might be more simpler, but it might depend on the station. Fourth, it is also important to check whether assumptions such as linearity are acceptable in terms of background knowledge. If it is acceptable to some extent, it should be okay, but otherwise it might be better to interpret the estimated causal graph as a reference. Okay, so what can we do after estimating the causal graph? So first of all, it would be a good idea to evaluate the independence between the error variables. If the error variables of a variable pair are not independent well, then it will suggest that we should add some more variables in the analysis as common causes between the pair of the variable pairs of the pair. It is also possible that error variable, of course, it is also possible that the error variables are not independent because the other assumptions are violated. So we may also want to consider relaxing the model assumptions. Also, the model assumptions are more or less violated in reality, so it would be better not make a binary decision of whether or not the null hypothesis of independence is rejected by the test. Next, in this paper, a method has been they have proposed a method to evaluate the estimated causal graph by the prediction accuracy on test data. Like ordinary machine learning approach. So this is based on the following idea. Once the causal discovery is once the causal graph is estimated, the Markov boundary can be obtained for each variable. And once we know the Markov boundary, it is known that we can make our optimal prediction using the variables in the Markov boundary. So we predict each variable with the variables in its Markov boundary and check the prediction accuracy over the variables. If the prediction accuracy is poor, it will imply that the Markov boundary is not estimated well, and then the causal graph will not be estimated well. So one thing to note is, since the Markov boundary can be obtained if the equivalence class is known, this method evaluates the correctness of the equivalence class rather than the causal orientation between variables. However, this is still useful. I think this is still a useful evaluation method to evaluate the estimated causal graph from various aspects, testing and prediction accuracy. Another idea would be to compare the estimation result with those of other datasets where the causal graphs are expected to be similar based on background knowledge. If the results are completely different, we might say that our assumptions were not very reasonable. Of course, we can also check whether the results are consistent with the background knowledge. And if not, we might want to relax the assumptions of the model, or maybe increase the sample size, to get better stability, statistical stability. Okay, so the next topic is how we evaluate statistical reliability. The most typical way to do this would be to perform bootstrapping. If the bootstrap probability of each directed path or directed edge is less than some larger than some threshold, larger than some threshold, then say 5% or more, we would say that they are reliable enough to interpret them. So then pairs of variables with larger causal effects would be more promising candidates to change the values of the effects. Okay, so also furthermore, we may want to find out what pathways exist from, for example, from this x3 to x1. Then it would be a good idea to compute the bootstrap probability for each path, and see which paths are statistically reliable. Here, x0 and x2 are they are likely to exist between x1 and x3. This kind of bootstrap analysis can be performed using the LiNGAM Python package available at this URL. Okay, so so then I will discuss how we could relax the model assumptions. Besides the LiNGAM model, other models have been found that the causal graph is uniquely identifiable. First of all, these nonlinear additive noise models or post-nonlinear causal models are identifiable. They have a nonlinear function here, fi here, and gi here. However, the error or noise ei is additive in the form of plus ei plus error. They are for continuous variables. They are for continuous variables, but there are also identifiable models for discrete variables. For example, they assume Poisson distributions. And third, this would be the this would be a more realistic setting where we have both continuous and discrete variables. And for example, LiNGAM, we assume a LiNGAM-like model when the effect variable is continuous. And we use this logistic type model when the effect variable is discrete. This paper showed that the identifiability of two variable cases, but I guess that the multivariate cases are also identifiable. It can be shown to be identifiable, I guess. Okay, so next, to improve the statistical reliability, we could use background knowledge in the estimation. For example, we sometimes know the causal order of some variables. For example, in manufacturing, we can often divide the variables into 3 groups. And we often know the causal order between the groups. So the first group is variables related to manufacturing conditions. The second is those related to intermediate characteristics. And the last is those related to final characteristics. So we know the causal order of these 3 groups, and we want to find the causal structure of this part, the causal structure of intermediate characteristics. If such a causal order is known and we use it in estimation, the results will get more statistically stable. For instance, in LiNGAM model, we can use such background knowledge in estimation, and also in nonlinear additive noise models. Okay, so another way to improve statistical reliability would be to use multiple datasets. We use some similarities of those datasets to improve the statistical reliability. Multiple datasets can be obtained by, for example, collecting data on the same set of variables from different populations or under different experimental conditions. Datasets from experiments with interventions are also acceptable. although they are different data sets, in many cases, the causal order between the variables will be considered not to be opposite. The distribution and the coefficients may be different, but the orders will be same in many cases. So we use this similarity in causal order to improve the statistical reliability by simultaneously analyze those datasets. Okay. So finally, I'd like to talk about some extensions to the case of hidden common causes. So first, I considered to estimate causal structures of variables that do not share hidden common causes. So let's take a look at the causal graph on the left as an example to explain the motivation. Here we have our hidden common cause F1 between X1 and X2, and we have hidden common cause F2 between X3 and X4. If we use ordinary LiNGAM, the result will be distorted because ordinary LiNGAM does not allow hidden common causes. So the first step is to find the variable pairs that do not have hidden common causes, and also those that do have hidden common causes. Then for unconfounded pairs with no hidden common cause, like X1, X4, we estimate the causal direction like this. And for confounded pairs with hidden common causes like X1 and X2, we leave the relationship to remain unknown like this. We connect them by this kind of bidirected edge here. So again, to find such a confounded and unconfounded pairs, again, non-Gaussianity and independence help find them. So as I mentioned earlier, if the direction of causation is wrong, not correct, the explanatory variable and its residual, they are not independent. Similarly, we can show that they are not independent also when there is some hidden common cause between the variables. So because such a hidden common cause, so like F1, introduce some dependency between the explanatory variable and its residual. Based on this, we can find unconfounded ancestors of each variable if they exist as follows. So here. So we first try to find a set of variables that gives independent residual when a variable is regressed on every its subset. So independent residuals, right. If succeeded, variables in such a set are unconfounded ancestors of the variables. We have shown this in this paper. For example, in this graph, we find that X1 and X2 are such a set of variables, and they are unconfounded ancestors of variable x4. We can find the unconfounded parent of variable x4 is x1. Similarly to this way, as we find the unconfounded ancestors. So we can find the direction between the x1 and x4. Right. So, okay, so here, I did not estimate the causal direction for variable pairs with unconfounded common causes like this pair, x1 and x2. We did not estimate the direction between the two. But we sometimes want to estimate the causal direction even for such confounded pairs. In such a case, we can use the following method I introduced now. This is a LiNGAM model with unobserved hidden common causes. So F is the hidden common cause vector, and lambda is the coefficient matrix. I don't go into detail here, but the hidden common causes can be assumed to be independent without loss of generality if we assume linearity. And if we solve this equation for x, then we obtain this kind of independent component analysis model. So this is because these error variables and hidden common causes are non-Gaussian and independent. And from the results of the field of independent component analysis, this coefficient matrix, this one can be essentially estimated. This coefficient matrix is called the mixing matrix in the field of independent component analysis. So, so here's as example, here are three models. So in the left model, x1 is the cause, and in the middle, x2 is the cause, and no relationship between the two variables. And f1 is hidden common cause. So if we write these three models, causal graphs, in the form of independent component analysis, ICA, we get these three. The point is that here, the the location of the zero is different in these three models. So we have zero here, and we have zero here, and we have two zeros here and here. So we use this relationship to estimate the direction of causality between the two variables x1 and x2. So this means that we first apply independent component analysis on data, and we look at the zero non-zero pattern of the elements of the estimated coefficient mixing matrix. Then we see the estimated zero non-zero pattern is close to which model. And if it is closest to the leftmost pattern, this pattern, then we conclude that this model best fits the data. Last but not least, we will discuss another LiNGAM model with hidden variables, LiNGAM for latent factors. In the previous model, we were not interested in the hidden variables themselves, but in this model, we are interested in the causal relationships of the unobserved variables. Here, we call the hidden variables latent factors. So we assume the LiNGAM model for the latent factors. Further, we assume that multiple measurement variables X measure each latent factor, like factor analysis model. And we also assume that at least two of the measurement variables are pure measurement variables. Here, pure refers to the case where the measurement variable measures only one latent factor. Then the model is known to be identifiable. As for the estimation, this is a bit kind of in development, but we do the following. So first we estimate the measurement model, the coefficient matrix or factor loading matrix G. Then we use the data and the coefficient matrix T to obtain the estimates of latent factors. Then we infer the causal relationship between the latent factors, this way or this way. This way or this way. Okay, we can also use multiple datasets to estimate the causal relationships of latent factors. In this model, we can also find such latent factors that appear commonly across those multiple datasets, and also those that only appear in some datasets. So the estimation is, this is how it looks like in the figure. We first extract latent factors for each dataset, dataset 1 and dataset 2. At the same time, we also estimate. After that, after we extract latent factors for each dataset, we infer the causal relationships among the latent factors, this way or this way, this way or this way. At the same time, we also estimate which latent factors in each dataset are considered to equal to those in other datasets. For instance, this latent factor is equal to this latent factor, or maybe equal to this one. We can do that. Further, if we expect some similarity in the causal structure, then we can incorporate them into the model, also in the estimation. In this way, we can simultaneously perform feature extraction and causal discovery between latent factors across multiple datasets. Okay, so finally, I summarized the talk. Okay, statistical causal inference is statistical causal inference is a fundamental tool for science. In statistical causal science, many well-developed methods are available when we can draw causal graphs with background knowledge. However, we do not always have sufficient background knowledge, so we can use data to help draw causal graphs. This is effective for causal inference to be used in a wider range of fields. Causal discovery I have talked about is a methodology for this purpose. The key settings for further development of the methodology would be first that there are hidden common causes or latent factors. Second, that we can handle both continuous and discrete variables. Third, to deal with cyclic structures, which may be one step further. That's all. Thank you so much.